Hello, class. I thought I would finish chapter 11 today. We didn't quite make it in class since we went over the exam 4 and what to expect on the final and how to calculate your grade and so forth. So I just want to, again, before we get started, just make sure everybody's kind of on board with Chapter 11. It's all about gases. And, what we've talked about is pressure, that's equal to a force divided by area. We talked about Torricelli inventing the barometer by putting a pool of mercury and then putting a glass tube that was filled with mercury, and the mercury flows out to a point, but it doesn't completely flow out, and that's due to the atmospheric pressure pushing on the surface, which keeps this mercury in the tube, and atmospheric pressure holds a column of mercury that's 760 millimeters high, and we can determine the pressure by the equation height times density times gravitational pull. And so then we talked about that. Then we started talking about kinetic molecular theory of gases. And so I do want you to make sure you read that and understand what the postulates are of this theory. And then as we progress through the chapter, I want you to relate those to Boyle's law, Charles' law, Avogadro's law, and then we had the combined gas law that we covered today. And again, know that this is, the general form of the equations I want you to memorize is this is P1 times V1 equals P2 times V2 for Boyle's law. Charles' law is V1 over T1 equals V2 over T2. Avogadro's law is V1 over N1 equals V2 over N2. And then the combined gas law is really just combining these three laws into one equation. P1 times V1 over T1 equals P2 times V2 over T2. We assume N is constant. The number of moles is held constant. That's why you don't see that in this expression here. So we spent a lot of time with that today. We introduced the ideal gas law, which is PV equals nRT, and then we derived from this equation, I'll put it over here, that density equals pressure times molar mass divided by the gas constant divided by the temperature. So we did a couple of equations with that as well. And that, again, is really derived from the ideal gas equation. So that's what we spent time on lecture today, and then I ran out of time. And you have problems like this in the book, and I would encourage you to go through this section and try, read it, and then do the practice problems at the end of that section. And then if you need additional work beyond the module, that you try the odd problems in the back of the chapter, and I think that will help quite a bit. We're skipping section 11.6 on the ideal gas equation, so don't worry about not covering that. So 11.6 is real gases. The reason why I skip this section is I believe you'll get it in physics class. Most of the time in chemistry, until we get into advanced chemistry, we assume ideal gas behavior. So I hope that helps. That's what we've covered up until today. So that's what I could cover. And so now I want to talk about what I didn't cover today, but can be on the final exam, and that is Dalton's partial pressure law. So this is section 11.7. This is an important section, especially those of you going in the allied health field, because a lot of times you'll measure blood gases and you'll determine the person's health based on these blood gases. So the thing that I think is important about the Dalton's partial pressure law, it probably makes sense to you. I think it's more about the terminology than anything else. So I have a container. It's a fixed volume. We're dealing with a fixed temperature, and we have a pressure gauge on here. So here's my pressure gauge. And again, if there's nothing in the box, we have a vacuum, and so the pressure would read 0 compared to the outside pressure. So I add atoms of A or particles of A. It could be molecules or atoms, and so we register pressure on the pressure gauge. And we have said that pressure is equal to force divided by area. So these molecules have motion, or these particles, and when they strike the diaphragm, that's a force transferred to the area of the diaphragm, and we get a pressure. So in this example, they have 1 mole of nitrogen gas in a 5-liter container, 0 degrees Celsius, and it exerts a pressure of 4.48 atmospheres. So just assume A here is nitrogen. Well, what happens when you add an additional mole of oxygen gas? So now we're going to put in a different gas. We'll call it B, which it will represent by the oxygen. So tell me what happens. If I add B into the fixed container, same temperature, what happens to the overall pressure in the container? And I bet most of you would say that the pressure is going to increase. How much is it going to increase? Well, there's a relationship between pressure and number of moles. So each gas is going to exert a pressure of 4.48 atmospheres. And you said, how'd you get that? Well, 1 mole of nitrogen gas times R times T divided by V. Same thing for the oxygen. Both of these have an individual pressures, or we call them partial pressures. So I think that's the first thing that confuses students is, well, you just told me what the pressure of the nitrogen gas is, and you just calculated the pressure of the oxygen gas. Well, we have a term for that, and that's called partial pressures, and the I stands for whatever substance you're measuring. So if oxygen gas, nitrogen gas, carbon dioxide gas. So just know that partial pressure is the pressure of that individual gas. So what do you think the total pressure is inside the container? Well, hopefully you know that you would add these two together and you would get the total pressure in the container. So this is PT, the total pressure. So the pressures of each gas are summative. So we call it the partial pressure of nitrogen plus the partial pressure of the oxygen gives us the total pressure of 8.96 atmospheres. Summative. That's pretty much all what Dalton's law is, and then you can start adding, different variables to it. But the bottom line is you have a fixed container at a particular temperature. You're adding moles of gas in. The more moles of gas you add in, the greater the pressures, and that these different moles of gases have different partial pressures, or different pressures, but they're called partial pressures. And that gives you can sum those together, get the total pressure. All right, so let's look at a picture of it, and let's just look at how we would write this mathematically. So real easy, the total pressure is the sum, that's what this capital sigma represents, of the partial pressures of each gas that's added to the container. So in our picture here, remember the plunger represents the atmospheric pressure, and the container represents our fixed volume. And so here is substance W for white, and this is what the pressure is. And now we're going to add substance R, which is the red, to that. Notice there's a lot more red, and so we see the pressure increase. Makes sense, right? So if we keep the volume the same, we inject more moles or atoms, either way you want to think of it, then the pressure, and we got to keep the temperature same, then we would expect the pressure to rise. Very important rule, though, very important, because, again, when we look at blood gases, we're looking at CO2 in your bloodstream, nitrogen, we're looking at oxygen, maybe there's some other gases there, and so we're looking at those gases to determine the person's health. All right, so let's look at it again. This is what's kind of neat about this is here you have a container, again, fixed container, and it says each component of a gas exerts a pressure independent of the other components. Again, this is for ideal gases only, and again, we are assuming ideal gas behavior, and we skipped the section on real gases. So here's the pressure due to the purple particles. Here's the pressure due to the yellow particles. When we add these together, these parts are additive, and we get the overall total pressure being the addition of this pressure to this pressure. And there's the equation right there. Very simple concept. I think most people do fine on this. I think it's more of a language thing than it is math. All right, so let's look at this question. It says you have a liter container vessel. So, when in doubt, if you're struggling on a problem, draw a picture. So I'm going to put my box here, and I'm going to say, okay, my box has a volume equal to 1 liter. And it has 0.215 moles of nitrogen gas, and it has 0.0118 moles of hydrogen gas. Determine the partial pressure of each component and the total pressure. So you want to record what you have. You have you know what R is, the gas constant. You know what the temperature is in degrees Celsius, which will have to be converted to Kelvin. And you know the volume of the container. So when you see these variables, you should be thinking, oh yeah, this is PV equals nRT, because we're dealing with an ideal gas. I'm solving for pressure, so pressure is equal to nRT divided by V. So that looks good. So now I take the information from the problem and place it into the equation. So there's my number of moles of nitrogen gas. There's the gas constants, which you'll have memorized. The temperature, 25.5. Again, make sure anytime you're working with a gas that you convert this to Kelvin by adding 273.15, and that gives us 298.65. Divided by the volume of the container. And here's what I want you to do to make sure you don't make careless mistakes. Before you touch the calculator, watch the units cancel out. Watch them cancel out. And you will see the only unit left after everything cancels out is atmospheres, and that is a pressure unit. So that's what's going to tell you, hey, I've set this problem up right. So what I hear students say, well, the pressure of the nitrogen is 5.27 atmospheres. Well, what I want you to say, to speak the language of chemistry, the partial pressure of nitrogen is 5.72 atmospheres. We do the same thing for hydrogen. What's the difference? Well, the moles were different, so we plug in a different mole. Everything else is the same, though. So the partial pressure with respect to hydrogen is 0.289. If I add these together, that's called the summation. That's why they gave you that sigma symbol. And that equals 5.56 atmospheres. That's the total pressure, which we generally just say capital P with a subscript T. Very easy problem. It's about organizing the data and solving for the unknown. Okay. All right, let's talk about mole fraction, because a lot of times we use mole fractions when we're talking about Dalton's law, and there's a relationship between mole fraction and pressure or partial pressures. So mole fraction, what is a fraction? A fraction is a component out of the total. So like, again, if we have a fixed container, and we have particles of A, 2 particles of A, and 2 particles of B, then what is the fraction of B compared to the total? Well, you'd have 2 B's divided by the total of 4 particles, because you got 2 A's and 2 B's. So that's a mole fraction. That would be 2 divided by 4, and you would get a mole fraction of 1/2. Okay? So mole fraction is the component you're interested in divided by the total number of components within the container there. And so it's symboled by this chi. It looks like a fancy X with an I here, and the I represents whatever mole fraction you're interested in. So if I'm interested in B, this would be the mole fraction of B here. So whatever you're trying to find the mole fraction of, that's what you're going to substitute in for the I there. All right, so here's what you need to remember. The mole fraction of a component in a mixture is always less than the number 1, all right? Just like this. The mole fraction of B is 0.5. That's less than 1. The mole fraction of A is 0.5. When you add up the mole fractions, the total has to equal 1. The sum of all mole fractions always has to equal the number 1. If it doesn't, either you've made a mistake or there's experimental error there of some sort. The other thing you notice is that when you divide moles by moles, the mole fraction is always dimensionless. There are no units for mole fraction. So make sure you understand these 3 rules. This is going to help you in solving more complex problems. All right, so here's the one that kind of throws students off. Mole fractions can also be related to pressure. So if we keep the temperature and the volume fixed, then think about it, PV equals nRT. And if all of this is fixed and we divide this by fixed volume, then we would see that P and N, if that's the only change, are equivalent to each other. So what I have there is all this becomes a constant, right? The volume's fixed, the temperature's fixed. So it's P equals N, and then all this over here becomes a constant. So because of that, we can say mole fractions are equal to the partial pressure of a substance divided by the total pressure. And you go, why do I need to know this? Well, when you're working with gases, generally that's what you're measuring is pressures. You're not weighing gases out because they're not dense like a solid or a liquid. And so they're generally in a closed container. And so they're in a container and there's generally a pressure gauge. And so you're going to measure mole fractions of gases by pressures and not moles. Now, can this be manipulated? Yeah, you can relate the mole fractions related to pressure to the mole fractions related to number of moles. So you could say Pi over the total pressure is equal to Ni over the total number of moles. Now, it's not exactly equal because you got to take into account to convert from number of moles to pressure, you have to know what the R, T, and V are. So that's a constant. So just don't forget it's not just Ni equals Pi. You've got to take into account the gas constant, the temperature in Kelvin, and the volume. So let's read this problem here. It says in 1999, the FDA approved the use of nitric oxide to treat and prevent lung diseases, which occurs commonly in premature infants. This is why I'm saying this is really important to allied health. And that's why I'm spending the time doing this video. Even though we didn't get to cover it today in class, it's worth knowing. That's why I'm taking the time to do this. The nitric oxide used in this therapy is supplied in hospitals in the form of nitrogen to nitric oxide mixture. Calculate the mole fraction of nitric oxide in 10-liter gas cylinder at room temperature at 25 degrees Celsius that contains 6.022 moles of nitrogen gas and has a total pressure of 4.75 atmospheres. So all this is derived from the ideal gas equation. And I said that in class today. I said, when we got the ideal gas equation, I said pretty much the rest of this chapter is going to be related to the ideal gas equation, PV equals nRT. So if I'm going to solve for N, I would get N equals the pressure times the volume divided by the gas constant times the temperature. So the total pressure, that's what I'm going to use because I'm trying to determine the total moles. The total pressure is given in the problem. You may want to write these down, like organize your data and say P total is equal to 14.75 atmospheres. And you do want to make sure you're looking at the units, because sometimes they'll be different. You got to watch your units carefully here. Sometimes these pressures will be in millimeters of mercury, and you're going to have to convert them to atmospheres because this gas constant is liter atmospheres Kelvin mole. So we have the total pressure. We have the volume of the container. That's fixed. That was given right here. We have the gas constant, which you've memorized. And then the temperature, yes, they give it to us in degrees Celsius, but hopefully by now you know you have to convert that to Kelvin. Before you touch the calculator, you watch the atmospheres cancel out, the liters cancel out, the Kelvin cancels out, the mole, which is in the quotient of a quotient, comes up into the numerator. It's just like this. Quotient of the quotient gives us that, right? So the mole here is in the quotient of a quotient, comes up here. So the moles of nitric oxide is equal to the total moles minus the moles of the nitrogen gas. Well, the total moles we just calculated because we based that on the total pressure here. So if I take the total moles, and then they told us we had this many moles of nitrogen gas, if I subtract that, that will give me the moles of the nitric oxide. So this is the partial pressure, right? We're saying, let's write it up here. The total pressure is equal to the partial pressure of the nitrogen plus the pressure of the nitric oxide. We just solved for we used the total pressure to solve for the total number of moles. And then we know how many moles of nitrogen we have. And so when we subtract that, we get the moles of nitric oxide. Now we have the moles of nitric oxide, and we have the total number of moles. We divide those, we get a mole fraction of nitric oxide as being 0.001. All right, the moles cancel out. We are finding the mole fraction of the nitric oxide, and again, it's a unitless value, and it's 0.001. So I hope that helps. I hope that, that this is showing you how you would actually apply this in real life. All right, this section, I think it's worth covering, and the reason why is this. One of the most important topics that you must learn in Chemistry 170 is stoichiometry. So we've had problems where you convert grams of a substance to moles of that substance. We'll say grams of A to moles of A to moles of B using our balanced chemical equation to grams of B. That's our typical stoichiometry problem. In the previous chapter, we had where you convert, you have a concentration of something, and you have the volume of it, and you could figure out the moles from that, and then you could also do the same thing. You can do a stoichiometry problem based on concentration of solutions times the volume of solutions. So this is like what you did in lab where you had a beaker and you poured in 50 milliliters of 0.1 molar hydrochloric acid, and you poured in 50 milliliters of 0.1 molar sodium hydroxide. And so that's a neutralization reaction, so you should know that terminology, that hydrochloric acid reacts with sodium hydroxide. Tell me what the products are. You should be able to tell me that it's water and the salt sodium chloride. So this equation's balanced, and then we could do this to do a stoichiometry problem. So in this chapter, we're not dealing with concentration units. We're not dealing with masses directly, we're dealing with gases. So in this equation, we do start with grams of sodium, and I would like to know how many moles of or liters of chlorine I need. Oops, let's go back. I want to know how many moles of chlorine or liters of chlorine I need for a certain number of grams of sodium. Okay, so any stoichiometry problem, bottom line is you have to have a balanced chemical equation. There it is. 2 moles of sodium solid react with 1 mole of chlorine gas, and that forms 2 moles of sodium chloride. So let's say somebody gave me 40 grams of sodium with a decimal there, so it's 2 significant figures. And I would like to know how many liters of chlorine gas would I need in order to react all of that sodium. So it's a stoichiometry problem, right? You started with the 40 grams. You know that you need to divide that by the molar mass so that the grams of sodium cancel out. Now you have the moles of sodium. And then here's the most missed part of all stoichiometry problems. I can't stress this enough. You need to keep going back and back to this. This is the most missed part. You get your mole to mole ratio from your balanced chemical equation. For every 2 moles of sodium consumed, 1 liter or 1 mole of chlorine is consumed. So my mole to mole ratio will now change that to moles of chlorine. That's the only way you can change from one substance to another is through your balanced chemical equation and getting your mole to mole ratio. Now, they asked for liters of gas, so you would say, well, liters, PV equals nRT, and then liters is the volume, so volume equals nRT over P. And so in this problem, you've determined the moles, so that part's known. You know what the gas constant is, so the temperature has to be given and the pressure has to be given. And if they don't give you the pressure, you assume you're reacting it at 1 atmosphere pressure in your beaker. But that's why they got multiplied by RT over P here to give you the liters of chlorine. So it's another practice for you to learn how to do stoichiometry. It's, like I said, this is like the 3rd different way we've done stoichiometry in Chem 170. But that is one of the most important concepts that you have to learn in this class. All right, so let's look at this one. It says sodium peroxide is used to remove carbon dioxide from the air supply in spacecraft. It works by reacting with CO2 and air to produce sodium carbonate. So we got a sodium peroxide. How do you know it's a peroxide? We've learned naming. We know if it's group 1, you see these double 2s, it's a peroxide. Reacts with carbon dioxide, forms sodium carbonate and oxygen. Watt volume in liters of CO2 at STP, that's something we learned today in class. STP is standard temperature and pressure. The pressure at STP is 1 atmosphere, and the temperature is 0 degrees Celsius, but you're going to convert that to 273.15 Kelvin. All right? Will react with the kilogram of sodium peroxide. All right? So tell me your plan of action. Think about your plan of action to solve this problem. What are you going to do first? So you should say, well, I want to take the grams of sodium peroxide, and I'm going to convert that to moles of sodium peroxide. Why? Because I've got to relate it to my balanced chemical equation. That's what stoichiometry is all about. Once I convert this to moles of sodium peroxide, then I can convert that to moles of CO2 that will be reacted. It's a 2-to-2 ratio here. For every 2 moles of this consumed, 2 moles of this is consumed. And then they asked us not for the moles, they want to know what the volume in liters are. So I've got to somehow convert this over to liters of CO2. And so to do that, I have to know, again, PV equals nRT, and volume equals nRT over P. And I'm going to assume, since they don't tell us the pressure, we're going to assume 1 atmosphere of pressure. All right. Well, we know that because it's STP. Yeah, there's where I messed up. STP tells us the pressure and temperature. That's where we have 1 atmosphere pressure and 273.15 Kelvin. All right, so there's my plan of action. It's a stoichiometry problem. You start with what's given, convert that to moles so you can relate it to your balanced chemical equation, convert it to your other substance using your mole to mole ratio. And then the kicker for this chapter is we're going to convert moles over to volume units. How do we do that? Using PV equals nRT. So next slide. There's where we took our kilogram, we converted that to 1,000 grams since we know the molar mass is in grams. This is how many moles of sodium peroxide we have. Here's our mole to mole ratio. It's 2 to 2, which is 1 to 1, so that's why this number didn't change. This is how many moles of CO2 that will be consumed. And then we plug that into PV equals nRT, solving for V. So there's N, there's R, there's T, there's P. How do we know these? Because it's STP, standard temperature and pressure. So that's really important that you remember that. And that's the way we solve the problem. So like I said in class today, it's pretty much using PV equals nRT many different ways. All right, determine the amount of reactant consumed using change in pressure. All right, so here we want to know the relationship between the number of moles and pressure. So they've taken PV equals nRT and solved for N, so that's where we get PV over RT. And you say, why did they pull this out? Well, a lot of times the volume of the container is constant and the temperature is constant through the course of the reaction. So any change in pressure means a change in number of moles if we're holding the volume and the temperature constant. R is already a constant. So the relationship between changes in number of moles and change in pressure is this equation. It makes sense, right? If you're measuring the pressure here and you went from 4 moles of A to only 2 moles, you saw a change in the number of moles and you would see a decrease in pressure. And the relationship to make this equal is all of this has to be a constant, volume over gas constant times the temperature. So let's look at application. All right. Another air purification method for enclosed spaces like a submarine is we take lithium hydroxide and it absorbs or reacts with CO2, forms lithium carbonate and water. Again, this is a thing about anything with a closed environment like a submarine. You don't really breathe out that much CO2 when you're breathing in air. Otherwise, if it was all CO2 coming out of your mouth, you couldn't do CPR. So the CO2 is what starts to build up in an enclosed space, and it starts making you nauseous and eventually can cause you to pass out and die. So if we can scrub the CO2 out, there's plenty of oxygen still in the air for us to live. So in this case, in a submarine, we have a fixed volume. The volume of the submarine is not changing. The temperature of the submarine inside the submarine, that's room temperature inside the sub. And the initial pressure that we measure is 0.997 atmospheres. What happens if the pressure in the sub drops to 0.9891 as a result of the carbon dioxide being consumed? All right, so this is the only gas we have here. If this is consumed, the pressure is going to drop. And so what we want to figure out is how much did the moles of carbon dioxide drop? So PV equals nRT, here's our equation. The change in number of moles is equal to the change in pressure times these constants. The volume of the sub is constant, the temperature is constant. So the first thing we do is we measure the pressure drop. The final pressure minus this is the initial pressure minus the final pressure. That tells us the change, all right? Then we had the volume of the sub fixed and the temperature fixed. We plug this in, delta in, the change in number of moles of CO2 is the change in the pressure times V over RT. Again, take the time to watch the units cancel out so that you know what you're doing here. And so let's see here. Yeah. And so that makes it the pressure. This is the pressure here in atmospheres. And that pressure and that pressure cancel out. And you're left with N. All right? Because there is an N there. I mean, that's the relationship. So we find out that 81 moles of CO2 has been consumed. Well, let's do it this way. Yeah. The moles don't count. The mole here pops up into the numerator here, and that's how we get our answer. Yeah, let's make sure we get that right. The moles here, because it's in the quotient of a quotient, there's our units there, 81 moles. All right, this one you might have done in lab. This is a common called gas displacement, water displacement reaction. We fill a container completely full of water, we submerge it in the water, and we take the bottom off, and so the water is completely filled in here. We have a reaction of potassium chlorate with manganese 4 oxide, and that generates oxygen gas. The oxygen bubbles up and it pushes the water out of the container. So when the water gets completely pushed out of the container, we know what the volume of the container is, it's fixed. And the pressure of the atmosphere and the pressure of the inside the container has to be the same. So we know what the pressure of the collected gas is. So the total pressure, though, the total pressure is the pressure of the collected gas in here. But the water has a pressure too. It's called vapor pressure, and it actually contributes to the overall pressure inside this container. So it's not just the pressure of the oxygen that's in here, it's also the pressure of the water. How much does the water contribute to the overall pressure? And it's not a lot, but it does account. So how do we know what the pressure of the water is? Well, luckily there's a table for that. And this table tells you at a particular temperature, this is the pressure due to the water vapor that is in that container along with the oxygen. So you look that up on a table, it has to be given. There's no memorization here or anything like that. So here it says calculate the mass of the oxygen produced, decomposition of potassium chlorate when 8.21 milliliters of oxygen is collected over water at 30 degrees Celsius and 1.1015 atmospheres. So we look at the table here at 30 degrees Celsius, the pressure contributed by the water is 31.9 torr. Now, here's the problem. Our pressure here is in atmospheres. The pressure here is in torr, which is millimeters of mercury. That torr is going to have to be converted to to atmospheres. You go, how do I do that? Well, at the beginning of this chapter, you know that 1 atmosphere is equal to 760 torr. All right. And they actually don't do that calculation, so that's kind of bad. They just left us high and dry there. All right. But what you have here, let's see. When 820 is collected over in 1.10. So all you're having to do here, if you want to know, if you convert this 31.9 torr to atmospheres, subtract it off the total here, that'll give you the pressure due to the oxygen, and then you can use PV equals nRT to determine the number of moles of oxygen, and then you use the molar mass to convert to grams of oxygen. I don't know why they didn't show that problem, but that's how you do the problem. All right, here's another one. Calcium reacts with water, forms calcium hydroxide and hydrogen gas. Determine the mass of the hydrogen produced at 25 degrees Celsius, 0.967 atmospheres, when 525 milliliters of gas is collected. So the partial pressure of the hydrogen is equal to the total pressure, the total pressure minus the partial pressure of the water. It's 25 degrees. You go back to the table. At 25 degrees, the pressure due to the water is 23.8 torr. So you're going to take your 23.8 torr. Let's write that down right here. 23.8 torr. And then you know that 760 torr is 1 atmosphere. And that converts the torr to this atmosphere. So you subtract that off. So this pressure is due solely to the hydrogen. So PV equals nRT again. We'll write it up here. PV equals nRT. N equals PV divided by RT. And there you have that. You have the pressure times the volume divided by R divided by T. That's how many moles of hydrogen you have. And the most common mistake I see here is that students forget, when you do the molar mass of hydrogen, it's got to be diatomic. So it's 2.016 for the molar mass of diatomic hydrogen. So we converted the moles into grams there. You do that. I hate to see students go all the way to the end here and not put the correct molar mass for diatomic hydrogen and get the wrong answer, because it would be one of the multiple choice answers. All right, to sum this chapter up, characteristics of gases, indefinite shape, indefinite volume, low densities, kinetic molecular theory of gases. There's different postulates there to read. So I'm not going to repeat all those. Molecular speed and diffusion. This was Graham's law. We talked about that. That was a couple of lectures ago. Gas pressures. We defined the units. Atmospheres is important. Torr, millimeters of mercury. Those are the main ones I want you to be interested in. Pascal is important too, because it shows you the direct relationship with the metric units. I'm not interested in bars, so don't worry about that one. Boyle's law, Charles' law, Avogadro's law, combined gas law. We talked about up to Charles' law in the second lecture. Today's lecture, we went to here. We're skipping this part, so don't worry about that. And then the lecture of this video was all of this part here. Notice stoichiometry again. So the stoichiometry really important. You're going to see it in 3 different places on a final exam, and so it's important that you get the stoichiometry down. It's that important. You don't want to get dinged 3 places because you just getting stoichiometry down, but that's important because that's what you need with you when you go into Chem 180. So I hope that helps, and if you have questions, email me.